All right. So I guess you are all able to see my terminal again. So I will go back from here and um, if I will again show you back where is the source code located and what I have copied. So to do that, again, remember the first step to go into the installation directory. I basically typed foam, which is the namespace, and I am back to the installation directory. Okay. And then I will basically go to the applications, cd applications, and then basic within that solver, and then basic. And as I showed you that I will be basically using this particular source code, which is a generic scalar transport form, which has temporal term, it has convective term, it has the gradient term and the diffusion term, all the term, and optionally it can also have some source and sink term. Okay, so I have already copied this into my folder, so which basically you can see in this folder as named as my scalar transport form. So what I have done is, so let me open it in terminal so that you can see. So you can see that there is a folder called my scalar transport form, which is nothing but the same folder that I have copied from there. And because I will be modifying it, I just, for better distinguishing it, I've just renamed the folder as my scalar transport form. Okay, and I will show you how we can modify it. Okay, so that's the first step. Once you copy the source code from the main repository, then you basically rename it as you want so that you can distinguish it. And let us see what is located within this. Okay, so if I go to my scalar transport form and then see that, like any other C++ code, it basically has a .c code or .cpp code, which is the primary C++ code. All right, and then we have a header file. So any in object oriented programming, what we do is the primary codes are associated with an header file, which incorporates all the declarations and definitions for the variables that are used in the primary code. So apart from that, to compile this, what we have to do is we have to have a make file, because we use make utility to compile the code. And let us see in the make file what is there. And in the make files, you will see that there is two text files. One is called files, another is called options, and there is a folder named Linux something, which basically within which your um, executables are located. And if I go to that folder, you will see that we have different things, right? um, which one of those is .o, right? And .o is the compiled executable files that is used while you run the simulation. So I'm not going into that, but what I'll do is now, I just want to assure you the fact that this is the folder that I copied exactly. I didn't do any modification yet. Apart from that, I renamed these .c file from scalar transport form to my scalar transport form, just so that I name it as a new solver. Because if you don't change the name, it will show you error while compilation, because it doesn't allow you to compile another solver with the same name which already exists. All right, so make sure about that. Because of that, you may get a lot of error if you don't change the name. So that is very important. So change the name of this main C++ code. And then before I start doing anything, before I show you the governing equation and what to change, I just want to clean it. Okay, because I've already compiled it before, so there may be some files which is remaining from the previous compilation. So what I will do is I will source the OpenFOAM again, because this is a new terminal, and then I use the command wclean. Okay, so make sure that you remember this command, because wclean is the command to clear previous compilations. Okay, previous compilations, logs and everything. And once I do that, I have exactly the same thing that I copy from the actual source code, and then it's my part to modify the code as I want and then compile it again. So let us see what is there in the header file and the main code, and let us try to modify it meaningfully so that we can understand what we are modifying and what we are expecting to see from it. Okay, so if I open the create fields.h, it is the header file, as I said, and it incorporates all the declarations and definitions. And you can see that first it says that in this scalar transport form, the main variables are actually t. T is one of the variables, and you can see the input of output object registry for OpenFOAM here. That this is the variable named t, and it's related to the runtime. Um, and so every runtime and time name, so every time step, it is either we read it or modify it or only read it, etc. So it can be only read only. Like for example, if you want to read the viscosity properties from the constant folder, we do not modify it because it remains constant throughout the simulation. In that case, it will be, I'll show you, it will be must read, but we do not modify it. But in this case, this is the variable, so we read it, also we auto write, which means that we modify going forward, we modify it, and it's also linked with the mesh field that we input. Then the next variable is u, which is the velocity vector. And then similarly in the object registry, we have linked with runtime and the mesh, and we also read it and modify it, auto write. Okay, then there comes the transport properties. Within the transport properties, as you can see in the object registry changes, as I said, within the constant folder, whatever there is the transport properties, which we read for calculation, but we do not modify it. So that's why it is not auto write, but it's no write. Okay, and then we have to read some scalars, which are like dimension scalars dt, which is the diffusion coefficient. And as you can see that it's the dimension of viscosity, and it is located in the transport properties. And we are also including other header files, which is available elsewhere somewhere in the OpenFOAM directory, like create phi.h, create fvoption.h, etc. Okay, so in this declaration and definition, let us not change anything, but we can change if you want to include a new scalar that you want to read. For example, you can add here, if you want to add a new variable, such as you for example, if you have a Navier-Stokes solver and you want to add a temperature field to your equation so that your solver solves both for velocity and pressure as well as temperature, then you can define a new variable here, which is a bit more involved and out of the scope of this session. But in this case, you can see clearly that we understand what are the variables defined, how they are linked to the object registry, and what are the dimension scalars that we read from here. Okay, so that we are not modifying at this stage anything. We are happy with this, but we will modify the governing equation, which is the main partial differential equation. So for that, I open the renamed code, which I named as my scalar transform.c. And you can see that this is a standard C++ code based on object oriented programming, right? So it has all the other header files that is needed, such as very generic fvcfd.h, fvoption.finite volume option, finite volume cfd schemes, simple control. So these are like header files which are used for any code, and it's very generic to OpenFOAM framework, so we add them. And then the primary code block starts by declaring all the arguments and everything. And then we add more header files which are like for to create mesh, create time, and so on and so forth. However, this is the primary header file which we can modify in this case. So the other header files are externally available and generic, and we do not need to modify them. However, for this particular case, the definition and declaration of the variables are located in this create fields.h, and which is in our hand. We can modify them, add new variables, new scalars, etc. Okay. But for this demonstration, I have not modified anything, just showing it that you have to include that header file here. And now the actual governing equation comes, and we include another header file which calculates the current number.h, which is the CFL criteria, the stability criteria for the CFD scheme. And you know that it is a function of the time step and the local cell size, and it has to be less than one in most of the incompressible schemes for the stability of the CFD solution. And then we start the simple loop. So as you know, that simple is the algorithm, that solution algorithm that we are using, and it can be piso or pimple also, but in this case it is simple. Then we do the time, like runtime starts, and we run a while loop for the whole runtime. Now within this while loop, we basically give another different arguments, such as we do non-orthogonal corrections, etc., etc. But interesting, the thing that we are going to modify is this part. This is the primary governing equation, which is finite volume scalar matrix T equation. Okay. And this T equation, what it does is, as the high level programming I presented before, it has the temporal term ddt of capital T, then div of phi t, this is the convective term, which is the divergence part. Then come the diffusion term, which comes from the Laplacian term, which is Laplacian of dt comma t. Dt is that scalar that we have read, the dimension scalar. And then we give equal to some finite volume options, which is additional source or sink terms can be added using this capability. Okay. So if we want to modify anything in here, we have to also modify relevant things. Otherwise it will show error, but it's a good exercise to, change one thing at a time and then see which error is coming and then commenting that part and do it. But after the T equation is there, we apply relaxation such as under relaxation. Then we apply some FB option constraint and then we solve it. So this stuff is basically the linear solvers are solved using linear solvers. And then we also use some other functions to correct it, etc., etc. Okay. So ideally, if we have to modify the governing equation, this is the block which is the most important part for us, where we can create different modifications. Okay. Now I'm just aware that I have 15 minutes, so I will show you quickly how we can compile, assuming that we have made modifications here. So this is a code. You can see that you can um, I mean, write and delete anything and modify this code. But be aware that if you change something, the corresponding header files need to be either added or commented. The corresponding variables need to be either added or commented, etc. So assume that we have actually modify something, because it would take me at least 15 more minutes if I modify it and show you. And I'm aware that I need to answer your question. So assume that we have changed this variable. For example, we have deleted the temporal part and the convective part and made it only Laplacian part. And from a scalar transport equation, we have made it a Laplacian solver or Laplacian equation. Okay. If we do that, then we will save it, and the main compilation stuff comes then. So we have to go to the make folder and we have to modify these files. So the text file named files, we will open it and we will see that the primary code name is there. Again, if this is something, the name that you are giving a new name, you have to change it here, otherwise it will throw error. If you keep it old name, it will try to use the old code and it will show up error. So you have to change the name of your code and also mention the new name.c here. And the interesting part is that in the exe thing, you see that normally this is foam underscore appbin, but I have added a foam underscore user underscore appbin, which tells the code that these compiled, executables or libraries will go to your user directory and will be saved in your user directory. And then I give the name of the executable, which is the same name I keep, but without the .c extension, because that will go as a .o extension mostly if it is an executable. So my scalar transport from .o would be the executable. So two important steps here. One is we have to add underscore user here to tell the code that it goes to my user directory, and we have to change the name of the new solver. Okay, that's done. And then the other file is options. So let us see if we need to change anything there. So what we'll do is do nano options, and you see that these are, so these options files, it actually gives the links to other executables which is generically available within OpenFOAM framework. For example, this gives to these lib files L finite volume, L FV option, lib library of mesh tool sampling, and also the finite volume mesh tool samplings ln include file. So this is the links that gets established with your new solver with the existing executables or library files that are available within OpenFOAM. Okay. Once we are happy with it, we'll come back into the previous path, and where we have the header file, we have the main source code, and we have the make folder with the necessary changes in the name. And the command to compile it is wmake, because if you can remember that we are using this wmake utility, or it's also used in this all wmake script when you compile the OpenFOAM. So if we do um, w clean, I mean, we used w clean previously to actually clean the previous compilation, then we use wmake, and that's it. So it's as easy as that. So you are now compiling the new modified code, assuming that you have changed your code as needed. For example, removed the temporal convective term and kept the Laplacian term, and it's successfully done. It might show you some error if you have not modified it correctly, or if you have not linked the correct library. But in this case, everything is fine. So it is important to see the last line. It says the path where it's actually located. So you can see the path, that this is not the path of my OpenFOAM installation directory, but this is the path to my user directory, where I have created this boss C, which is my username hyphen v2306 is my user directory. And that has a platform folders. Within that, it has created another Linux folder within that bin, and within that bin I have the new executables, which is basically, let's say, assumingly my new solver, its executable is located. Now what you have to do is, when you run your solver in the control dict file in the application, you have to give, instead of scalar transport form, you have to give my scalar transport form. Okay, so that's so that's basically a generic way of basically kind of compiling, taking the code from the source code, modifying it, and then using and making your own code. So with that, um, I'll just um, I'll just try to put um, put the basic steps here, and I'm happy to start the Q&A and answer your questions. So I had much more thing to tell, but again, time is limited. So I will just keep this. Can you see my screen? Not yet.
Yeah, I think you turn on your screen. It's not share
Okay.
yet.
Yeah, I'm sharing from my laptop basically. So um, yeah,
Yeah.
yeah,
Now it's okay.
yeah. So I will keep this slide that summarizes basically the process that I showed you, that we have the w clean and w make comments to compile a new code. And from the original code, we have form app bin and form lib bin, but we change it to form user app bin and form user lib bin for creating my new solver in my new user directory. And the workflow goes like that, right? So we have the main code, which is the new app.c, and then we have the header file nc.h, etc., etc., and we have the linked libraries through L option and I option in the options folder. And what we do is, and the folder looks like that. The new app will have new app.c and new other header.h, and the make file will have files and options. So when we rename our solver and do all the necessary modifications, we change the files, then change the name there and the path there, and then we make sure that all the um, I option and L option are correct with the existing executables and libraries, and then we do wmake. And then the new executable will be located in the bin folder in my user directory. So with that, yeah, I open the floor for questions if you have any.